Okay. Well, welcome. Thanks everybody for joining. I do appreciate it. Just a couple things to start off with. I did mute everybody as they came in, and I know some people have been chatting a little bit, and that's perfectly fine. But I would ask that as we move on, that you keep your lines muted, just because there's enough people on this call where it can get a little cumbersome to kind of keep moving. And I have time specifically at the end of the session. This is scheduled to go a little short, so that we have time for discussion and questions at the end. And then if you have a question come up while I'm presenting, feel free to chat, send it to me in the chat, and that way I can address the questions that come up throughout the presentation. Um, Personally, if I'm presenting in person, I love to like have conversations and discuss as we're moving along. Dane just chatted. He said he'll be monitoring them as well. I like doing the conversations as we go along, but WebEx makes it so much more challenging to kind of have that conversation. So, just a little bit about me. My name is Jason Beck. I am the North America Temperature Product Manager for Rosemount Temperature Products. I've been with Emerson for 5 years, so I work at Emerson corporate office in Shakopee, Minnesota, which is just outside of Minneapolis. I've spent my entire career at Emerson in customer-facing roles, whether I was in our inside sales engineering force for the continental U.S. or the last couple of years I've been working in our customer solution center, so bringing customers in, walking through the entire Emerson portfolio. So I have a very, very broad experience with all of Emerson's products, not just Rosemount, and definitely not just Rosemount temperature products. Uh, Emerson has a very, very strong safety culture, and so I just wanted to touch on a quick safety moment before we get going. I know here in Minnesota, we're still under stay-at-home orders due to the COVID-19 pandemic, and it varies across the country and across the world. But as we're spending more time at home, it's good to identify some common household hazards that you may not notice normally, just because you're not spending as much time at home. Um, I like to think of checking for trip hazards, faulty wiring, sharp corners. Or I know I've had roommates who like to place candles underneath paper lampshades, and that's a situation that's rife for problems. And I'm kind of continuing the fire theme, checking all your smoke detectors, making sure that those are up to date and connected and still functioning correctly. And then making sure that all your household members aren't putting candles under lampshades and other things like that. So part of a safety culture at work is also extending that safety culture at home, and it's just something that we at Emerson really look to. But diving into temperature measurement points, so I kind of want to cover briefly a traditional temperature measurement application, just to kind of talk about what it takes to design one. And then I'm going to go into a pretty good deep dive on our Thermowell Design Accelerator, including a live demo. So we'll go out to the website and we'll go over it and take a look at it, and then talk a little bit about some of our alternative technologies that the Thermal Design Accelerator can highlight or select for you to use. So that being our Twisted Square Thermowell and our Xwell temperature transmitter. But talking about a traditional temperature application, you're really looking at three components. You're looking at a thermowell, and this is essentially the protective sheath, generally made out of metal, but some of them, I know there are some applications that use PFA or PTFE, and this is protecting the actual sensing element from the process. And it's also transferring that heat, that energy from the process into the sensor so the sensor can measure. So there's a lot that goes into a thermowell to make sure it is the right length so that it is not being affected by ambient temperature, that it is long enough so that it is measuring the correct temperature, but then not too long so that it's not subject to vibration and it's not subject to wake frequency. And that's going to be a big topic of discussion as we move on. And then the sensor itself, it's going to be commonly an RTD or thermocouple, and that measurement technology selected based on temperature range, what accuracy you need. Or is this a monitoring or control application, or even a custody transfer application where you need very accurate temperature for density calculations. Um, what sort of vibration resistance do you need in your sensor? The length, okay, does it need to be calibrated? And then coming down to plant standards. I mean, some facilities are standardized on a specific technology, whether that's a given thermocouple type or an RTD or a certain type of RTD. And then when it comes to transmitters, so a lot of the debate with transmitters is, do I use a transmitter or do I wire direct back to a PLC or a multiplexer? What are the performance benefits of a transmitter? What sort of diagnostics do you get with it? Is it a local indication point? Transmitters come in different housing styles. So there's a lot of different things to consider with a transmitter and whether or not you're wiring direct. So these are kind of the three common considerations or parts of a traditional temperature application. Now I talked about Thermowell a little bit, but really diving into the Thermowell, is it what type of mounting style do we need? Does the process conditions, whether it's the static pressure or the actual process itself, or where it's getting mounted, does it need a flange? Does it have to be threaded? Do the piping codes call for a welded? Does it need a weldolet, or is it a weld straight in? What sort of profile is it going to need? What can I do to decrease the response time and increase the accuracy while still making sure that stem conduction error is not a problem, while making sure that it's long enough for those benefits, but not inducing vibration or susceptible to vibration. Material selection based on the process. Is it, do we just need a stainless steel one, or does it have to be PFA or some sort of nickel alloy or carbon steel? There's so many different materials that we can make thermowells out of. When you do install a thermowell, you're working with thermowells, you do need to shut down the process. So planning for the process of or planning for that process shutdown takes time. And then, other manufacturing tests, whether it's material traceability or an actual positive material identification, things that need to be considered when you're designing a thermowell. Now, focusing specifically on wake frequency calculations, when we're talking wake frequency calculations, generally we're going to refer to the ASME Performance Test Code 19.3 TW-2016, which is just an alphabet soup of letters and numbers. Going forward, you'll probably hear me refer to this just as the PTC, as it's a lot simpler to say. But this is the most current revision of ASME's performance test codes with relation to thermowells. And this provides a mechanical design standard to ensure safe and reliable thermowell installation and thermowell design. And this comes down to, ultimately the PTC, really it's a dimensional standard. What the output of the PTC is dimensions of a thermowell that should conform to your given process. And that comes down to, there's gates that the thermowell has to fit into. So it can, the PTC doesn't apply below 2.5 inches, for example. So if your thermowell is too short, then we're not even you can't do calculations to these codes. And conversely, if it's too long and it's going to be subject to too high a vibration, then you also couldn't do calculations. So there's a dimensional gate essentially around length and thickness, and has to be made out of round bar stock, and there's the dimensional mechanical standard. But then you take that standard and those dimensions and you run these calculations. It's a series of 4 primary calculations, and I mean there's a lot going on in the background to get to these, but these are the 4 kind of outputs. And the first one is the frequency limit. So is this thermowell going to be vibrating at a frequency that is in any of these keep out regions? Is the natural frequency of that thermowell at the flow velocity going to subject it to too much vibration? And then looking at the dynamic stress limit. Now, there are some regions where you can operate a thermowell where you actually pass through the first region and you get into that middle zone. And just if you think of like a popper soda can, and you just wiggle that tab back and forth, it doesn't take hardly any force, and eventually it will just fatigue and then break off. Um, and we want to make sure that we're not going to approach that dynamic stress limit if you're going through that first region. And then when it comes to static stress limit, all of these fluids, even air has a viscosity and a density, and it's going to be applying a force along the thermal well, and we need to make sure that the thermal well itself can withstand those static stresses. And then also looking at the pressure limit, is the external pressure, the static pressure of your process going to exceed the ratings of the tip thickness and the shank thickness? So running these four calculations is the primary drivers behind the PTC. So when you take all those into consideration, you take those three, segments of a traditional temperature measurement point, and you look at the thermal well. The thermal well represents about 75% of the total engineering effort by a customer or by a vendor doing customer designs for a customer or an engineering company. Um, the 75% of that design times goes into those wake frequency calculations to the PTC, goes into that selection process, making sure we're meeting um, the applicable codes in the area for piping. Uh, Almost all of that variability and unique points are in the thermal well as the process varies throughout the plant, and versus the sensor, which is really, once you have sensor technology selected, it's just making sure that it's long enough to contact the bottom of the thermal well. And then the transmitters tend to be even far simpler than that, as all we're doing is interpreting the sensor data. So it comes down to a bit of configuration and making sure that all hazardous area approvals are in line. It's the right communication protocol. But when it comes down to transmitters, the variability is much lower than it would be, say, for a thermal well. So really what it comes down to is that thermal well design is complex and time intensive. So Emerson has developed our thermal well design accelerator, and the idea is that this reduces engineering time for thermal wells by up to 95%. And I know you all had some issues getting on the WebEx today, as it's not an approved application. You had to download something, and that took some time. And so taking some things like that into consideration, we've designed this to be an online tool so that you can access it through a web browser. You don't have to download anything. It's just a portal. No software to install, no software to update. Uh, it's a strict adherence to the PTC. So I've taken questions from some customers about like, well, why can't I do a wake frequency calculation on my thermal well? It's like, well, it's outside the scope of the PTC. In the case that I'm referencing, the thermal well was too short. I think it was something like 60 millimeters. And if it's less than 65 millimeters, then the standard doesn't apply just because it's outside of the scope of what can be calculated. Um, and so the software itself, and I'll talk about this a little bit more, will actually say, hey, I can't do a calculation because you're outside the scope. And part of that having a cloud-based software that you access through a web browser is that the software is always updated to the latest revision without you having to download more information or have an update pushed to your computer. Again, IT and IT security is a big consideration, and that's part of it. We designed the software to allow mass uploads, so you can do one at a time and kind of walk yourself through it, or you can fill out an Excel spreadsheet and do up to 500 tags at a time. And this just allows for large projects. Maybe you're doing a plant expansion. Part of that, I didn't mention this earlier, but we calculated that the time to do a temperature design point is about 14 minutes. So if you're doing a large facility and you have 500 tags times 14 minutes, that's a lot of time. That's a lot of engineering effort to go into this. And so that, if we can reduce that by 95%, we can do it with 500 tags at a time. That's a huge cost savings just in a matter of time. We can do up to 18 process conditions per tag. So we know that different process conditions or different measurement points are going to experience different process conditions at different times. And we wanted to allow the flexibility to do multiple process conditions. And this is also how we could say calculate for two-phase flow. So if you have a mixture of liquid and gas, what we would say is that you have, excuse me, you would calculate for 100% liquid and 100% gas, and then you have the worst case scenario of both of those, and that's how you could do two-phase flow with this tool. So we allow up to 8 process conditions per tag, and that helps as you go along in doing these calculations.
Hey, Jason, I'll
Yes.
jump in. We got a good question from Tyler here. If
hmm
you're doing 500 tags for a job, are you able to leave the browser and come back into it and not lose any data?
So I think the question, if I may restate the question, uh, if you say start a calculation and you close out of the browser and you shut down your computer and say walk away, can you restart your computer and come back and the calculation has completed? Um, if that's the question, then I'd have to double check. Uh, I believe that you have to, I believe it would run the calculation in the background because once, I mean, everything is all cloud on the cloud, so it's not necessarily, your browser and your computer is not doing any of the calculations. Um, I'm gonna have to follow up on that one. Make a note of that real quick. That's a good question. Were there any other questions that were relevant right now?
Nothing yet.
Okay. Um, Probably the coolest feature of this software is the automatic reiteration of tags. So in previous softwares that we've used or previous tools that we've developed, you you would create a Thermowell or input dimensions into what would look like a very similar spreadsheet, and you would send it off to us, or you'd send it to Spartan, and they would send it to us, or you'd upload it to a design calculator and it or a wake frequency calculator. The calculator would do the calculation, and it would spit out a report that would say your frequencies here, your dynamic stresses are here, your static stresses are here, and it would say passed or failed the the standard. And then you have to make the decision on how to make changes to your dimensions to then re-upload it and try to get it to pass. This tool will automatically reiterate until it finds a solution. So it starts with base geometry, and then it will go through following standard practices until it finds a design that they'll pass the calculator. And then once everything's done, you're left with a series of dimensions. Now what do you do? And this, in our case, it outputs Rosemont model, Thermowell, and sensor model code so that you're ready to go and can hit the ground running with a Thermowell right away. I'd mentioned that it's a dimensional standard and that sometimes the you may be outside of the standard via just based on the Thermowell being too long or too short or some other differences. As you're entering the data, the software is going to kind of help guide you towards where it may have gone wrong. And in the example on the right, the Thermowell was sticking out the end of the pipe by about 60%. So too long, had to shorten it up, but it's giving guidance and we're trying to make it so that it's easier to make sure that we're fitting into the standard. When it's all said and done, you can get an unofficial analysis report, and this kind of is a way to say, hey, we have a valid Thermowell, we have a document with all the information. Now we can move into hopefully a quoting and purchasing phase before, you know, before we get to a point where it's like, hey, we've already written a PO, let's do some calculations, and now you have a failure and you have to go back and revise a PO to change a model number or something like that. We want to get all this information done up front to make that process much, much faster. And then finally, if it can't come to a solution that meets the uh, meets the PTC, we have alternative technologies that we'll try and make sure that it works. And so the first one we would try would be our twisted square thermal well, because if you're doing thermal well calculations, the idea is that you would use a thermal well, fastest reaction or response time, greatest accuracy, and so we'd look at an alternative technology like a twisted square thermal well, which is a wake frequency suppression thermal well. And if that doesn't work for some reason, then we would start looking at our Xwell, which is a non-penetrating technology. And I'll cover both of those here in just a little bit. I had seen a couple chats come in. I want to check those real quick.
Jason, actually, quick question about that. So
Yeah.
the software doesn't automatically go straight to the high tier Twisted Square or Xwell. It'll do the iterative process to try to make a standard Thermowell work first, correct?
Yes, yes. So the idea, and actually, Dane, you're getting putting the cart a little bit ahead of the demo here. I do have I'll cover that specifically in the demo.
Right on.
So, but that's a very valid question. All right, I'm gonna flip over to my web browser here. So this is the actual Thermowell Design Accelerator, and this is tied to what we call our My Emerson system. So this is tied to our online store. This is tied to some new flow calculators, and I know in Canada there's some question marks over how this will be accessed in conjunction with our partners up in Canada, but that's how this system is set up right now. Um, but this is the landing page when you first get here, and we have these two creation buckets. You can create a project manually, so that's where I mentioned you could go in and you can kind of enter line, item by item, and it's a graphical interface, and it's really straightforward, really easy. It walks you through how to input it, or you can create using a template. And the template is downloaded right on the page right here. So I'm going to click on that template because I want to show you all real quick. And this should look pretty familiar to anyone who's done wake frequency calculations before with Emerson or really with anybody. Um, you know, when we come down to it, fluid specification and is the same, pipe specification and geometry is going to be the same. The dimensions, these are all based on the PTC standard. And so, everything here is going to be really similar to what you've seen before. And as you're filling it out, you do have to fill out the header. This helps us follow the template or make sure it gets uploaded to the same place. And then we can come down here and you can input a tag. Uh, you can name your process condition and then your fluid description. So what is the name of your fluid? And then we start to get into some drop downs. So is this liquid or gas? You can enter the viscosity, and all these dimensions can be changed using drop downs between commonly accepted imperial or metric dimensions. We can change to DIN standard pipe if we wanted to. Over here. And nozzle dimensions, whether they be inches or millimeters. Probably one of the really cool things is that if you have a Rosemount model number already, you can select yes here and input a model code and not have to worry about the dimensions of the thermal well. So if you already have something, say you have a thermal well in the field that you've never run a calculation on, or maybe you have a scenario where you're breaking RTDs or thermocouples pretty frequently because you think it's got a lot of vibration and you have a model code in the field, you can go out, look at that tag, input it right here, and run a calculation pretty easily and not have to worry about all the dimensions. That's pretty straightforward look at the spreadsheet here. And we can go to the end. We can put in sales order line number. This is what we would put in. This tool is what we are using to upload data to do calculations for certification. So we have a SO line number, sales order line number on the end. You can put remarks in, notes, and just it's pretty robust spreadsheet. I'm going to close out of this. So once you upload that, I'm gonna skip the upload process and a bit of the calculation process today, just because with the WebEx on my Wi-Fi, it tends to push it just a little bit too far, and it takes too long to run all the calculations while I'm doing a WebEx, just because there's so much information getting passed back and forth. But this is what the upload would look like. You can see it imported the tag numbers here. We haven't calculated anything yet, so there's no calculation. I'm going to click on tag 6, and we're going to go look at this one. So tag 6, we ended up putting in 4 different operating conditions. You can scroll down. You can see this is where this pipe specifications came in, the Thermowell specification. And as you're inputting this data, it actually generates a graphical representation of the Thermowell that you currently have. And this is just a great way to kind of take a quick check and say, okay, yeah, that is a tapered, a threaded Thermowell. I know about what my nozzle is. I know about what my pipe ID is. You know, it gives you a really quick visual check of what you're looking at. And you can scroll down and you can see you could save changes, run a calculation, or reset back to the original. So let's just say, you know, if we hit calculate right now, we would run calculations. Again, I'm going to go to a project that's already been calculated just to save time. I like to call this my cooking show routine. You know, you think you're watching a cooking show like a Martha Stewart, and she dresses this beautiful turkey and gets it all ready. She puts it in the oven, and then 30 seconds later, she pulls it out of a second oven, and oh, voila, it's already cooked and ready to go. So that's kind of what we did here. This is something that I calculated earlier, and you can see a couple different indications here. So tag 1 passed on the initial calculation, came through, gives us a tapered Thermowell and sensor. Pretty straightforward, nothing really to worry about. Tag 2 failed on the initial calculation and then passed on the final calculation. Now we feel that it's important to distinguish. You know, we could just say, hey, it passed the calculation and not really say was it initial or did it go through iterations. But this is important because if you submitted geometry on a Thermowell or an initial Thermowell, and then it failed the initial calculation but eventually passed, it's important that you can visually see right away, this is no longer the original dimensions that I had. Something has changed here, and if that's relevant to your process or it's relevant to what you're working on, uh, it's good to know that right away so you can go in and make those changes. Same with tag 3, failed and passed. Tag 4 passed initially. Tag 5, so in this case, the calculation failed and it couldn't find a solution with a traditional Thermowell. So it says couldn't find a Thermowell solution. We recommend our Xwell. So in this case, it gives an Xwell model number, both the sensor and transmitter. And then tag 6 passed, failed initially and then passed. And here it gave us a twisted square Thermowell um, and Xwell. And I want to go into this one because this was that tag 6. This one had the multiple process conditions. So as we scroll down, you can see that there's a couple different things. I did see Taylor just sent a question in. I'm going to be able to cover that specifically when we get to the twisted square section. As we scroll down, there is again, change the graphic to update to show that it's a twisted square Thermowell. Now that we have calculations, we have Thermowell is acceptable for process conditions. We can show logs. So this shows that it has passed all 4 of the calculations that the PTC requires. It shows that the dimensions pass the PTC. Because it's a twisted square Thermowell, there is no frequency ratio. We don't do those calculations. And then it shows the 4 process conditions. I want to click on the tags results analysis because this is one of those where it went to a solution that I didn't want and I went back and I made a change. So in here, We did 184 calculations just on this one Thermowell. Now, if you can imagine, if you had to go back and forth with a calculator that was saying yes and no, and you went through 184 revisions, imagine how much time that would take and how much money that would cost you just in terms of person hours as you're going through those calculations. Um, but we can scroll all the way down. We can say, oh, looks like it passed on 3 different process conditions, but it failed on one. And so we can scroll up and see that, okay, it started by decreasing the unsupported length, and it started at a protrusion of around 55%. Okay, that's interesting. And then every single step here, it looks like it's decreasing the unsupported length. Now, what the software is going to do is it's going to go down to about 20%. So in this case, this started off as a tapered Thermowell. And so we get down to about 20%, and this is where we get to the minimum of what the PTC would require for protrusion length to run wake frequency calculations. And once we hit that minimum, it starts varying the root and tip diameter. So it's increasing the root and tip diameter until it can find a solution. So here it is, it's increasing it, it's increasing it. Keep going up, keep going up. So it got to a point now where, okay, we couldn't find a root and tip diameter dimension that worked with our nozzle. So let's switch to a twisted square. And in this case, the twisted square has 2 different root and tip diameters. So it started with the 0.75 inch, and that didn't work. And then it went to the 0.875 inch, and that also didn't work. And so now it's going to start decreasing the protrusion length. So the only reason that a twisted square wouldn't work is if the flow rate was so high that the bending stress on the thermal well was too much. So it's going to start decreasing that length until it gets to a point where it's either too short and it's not passing process conditions, or it's not going to work. So in this case, it then said, okay, the twisted square is not going to work. Let's try Xwell. And so it went in and, well, obviously Xwell is going to work because it's not penetrating the process, so you don't have to do any calculations on it. And I said, I don't really like that. Let's go back and look. And I made a change to the process condition. I think I had fat fingered something like 60 meters per second of process conditioned in that startup mode, and that's why it could never pass. So when I made that change and I changed it down to 6, it was able to pass using a twisted square. But all of that calculation history is here, and you can go back and you can see that all of it is there. You can see what the software did. It allows you to track and see what's happened, and so it's not just happening blindly in the background. So I want to go back to a couple things here. So I think there was a question earlier, does it jump straight to our alternative technologies? No, it doesn't. It's going to do its best to find a standard thermal well that meets that process condition. And if it can't find a standard thermal well, it's going to try our twisted square first. Because we assume if you want a thermal well, you want a thermal well. And so we're going to try to find a thermal well before we can do anything, or before we go to another alternative technology. And if it can't find that, then it goes to our Xwell technology. So back to our dashboard. Again, we were able to arrive at a twisted square here. These are all standard tapered thermal wells. We can click on this model number, and it's going to bring up a model number description. So we can see what all the dimensions are. We can see what the root and tip diameter is. We can go over to the sensor. Right now, it only selects thin film RTDs. As a future enhancement, we're going to set it up so that if you have a company standard that you like to work with, we can set it so that your company standard sensor is selected. But for now, it's just thin film. So just keep that in mind, that you would want to make sure that you're using the right sensor, that you make some changes if you need to. You can click here and go to product details, and it brings you out to the product page. Tells you about it. And then if you wanted to go a step further, you can go into configure, and this takes us to our online store. So in just a couple clicks, we can get pretty far into the system. Let's see. If you wanted to add more tags, you can add more tags to the system. Click on that plus, and it brings you to that graphical interface. So this is what it looks like when you're just entering a tag manually. You can select your shank style, pipe size, all of this is readily selected. And I mentioned that graphical interface. So this gets updated pretty quickly. So if I wanted to switch to a flanged, it's going to update almost instantaneously. So you can continue to have that quick visual inspection of, okay, does this match what I think I'm selecting? So I think that's all I have. Are there any questions specifically about the software while we're still here looking at it? I'm going to pull up my chat window and see if anything has come up. Okay, so no chats have come in about the software. I will say that I'll get this presentation and we'll have this recording available. So if questions do come up, feel free to reach out to your contacts. Um, and if they can't answer the question, they'll reach out to me and we'll make sure that we get you, we'll answer any questions that you have on the software or help anything, or when it comes to wake frequency calculations or the performance test codes, we'd be more than happy to help answer any questions. All right. So I had mentioned that it will try twisted square first. Oops.
Be worthwhile just to go through what's some more how someone would access the software more like search terms or something like that.
Dane, your audio is really broken up, but I think you asked how would they go through accessing the software?
Yeah, you hear me now.
It's still bad, but I can answer that question. So I would go Emerson Thermowell design Accelerator, and I would just Google search it, and then the first hit is going to be the login page. So the best way to access it is to go through there, and then this is where you can register to get a My Emerson account. And then we'll go through and verify your email address and send you a link to be able to access it. I believe this is the link straight into it from that page. So as you scroll down here from the software overview, you can scroll all the way down and get to the software just at the bottom. So it's very easy to access from our website. And as much as I would love to tout our website and how good it is, the best way is honestly to Google search, because that's almost going to be almost always the first hit, and it's going to be the fastest way to get to anything on our website. Don't tell our website people that I told you to do that, though. So yeah, back to the twisted square Thermowell. So I'd mentioned that the twisted square Thermowell, we actually don't do the calculations on frequencies for the Thermowell because this suppresses it so much that we don't have to. And we have some test data that can show that. But really, on a normal thermal, what's inducing those vibrations are these parallel vortices that are getting shed off the thermal. Now, because they're parallel with the thermal well, and they're kind of shedding off left and right at the same time, it induces that vibration. So the thermal well starts vibrating first fore and aft along the axis of the pipe, and then as the velocity gets higher, it'll start vibrating transverse to the pipe. Now what the twisted square does is, due to this twisting motion, is it converts those parallel vortices into perpendicular vortices. So it sheds them off like this, and it negates the induced vibration into the thermal well. And there's a couple videos, and I can send you links to those videos. Actually, they were on the Thermowell Design Accelerator website that show just how violently a thermal well can vibrate in a pipe and then how effectively this suppresses that vibration. I think there was a question kind of about a price difference. Um, I would I would talk to your Emerson sales representatives to know exactly what percentage the price difference is. I can tell you that because it's a proprietary technology, and honestly, the manufacturing process for this is quite involved. There is a price differential, and it is more expensive than a traditional thermal well, but it would vary by application, and I don't have a percentage that I can quote you specifically right now. I'm just going to erase these real quick because they will not be relevant to the next part. All right. And so then moving on to our Xwell technology. So I'd mentioned that this is non-process penetrating. This clamps to the outside of the pipe, and we measure the temperature at 2 points. We measure it using the surface mount temperature sensor. So we're measuring the pipe surface temperature, and then we're measuring the terminal block temperature up in the head of the transmitter. This allows us, because we know this is a fixed distance here, of the stem of this temperature sensor, we can calculate the heat flux coming up from the pipe, knowing the pipe material, and then the heat flux of the stem of our RTD here. We can calculate what the actual process temperature is to a pretty high degree of accuracy. So even though we're not measuring what's inside the pipe, the value of the temperature that we're outputting is considered a process temperature. So using this compensation in the sensor head and using this algorithm, we can get to within 1% of the difference between the ambient and the process. So if you have, say, a 25 degrees C ambient temperature, so just think air temperature or normal kind of standard temperature inside a building, and you have 125 degrees C process temperature. So say saturated steam, maybe it's building heating steam or something like that. Just as an example, then the difference in temperature is just going to be plus or minus 1 degree C at that point. So the accuracy of that internal temperature is just plus or minus 1 degree C. So this is really beneficial in a couple different applications. It's really fast and easy to install. It's only a clamp, which means no cutting or welding into the pipe. Pretty easy maintenance. Uh, I know we have a customer here in Minnesota who likes it a lot because it's faster and easier to install. They don't have to do a shutdown. They only need an instrument tech. They don't need a welding technician. They don't need to get scaffolding out there. They don't need to do going through the whole process of shutting down the pipe. They can put these almost anywhere. Uh, and it's non-intrusive. There's no leak points. We don't have to do a lot of material matching if you have a fairly nasty process. It's just bolt it, clamp it on, and go. You're able to move them as well once they're in the process. And if you're doing some design work and you're late in the design process and you don't have time to add a thermal well, maybe the construction has already begun. You could add this as a retrofit later on, or near the end of the process. And I am showing a wireless version here, and I've kind of talked about some wireless stories, but it is also available in our 3144 wired version. And then obviously, because it's not penetrating the price, there's no calculations needed to be done, and it makes it very, very simple and easy to get to. So this has been used on a couple different applications, specifically we've done it on heater exchange applications, pressure safety valves, diesel stripper tower feed lines, compressor discharge temperatures. Really, the main limiting factor to this right now is it does have an upper temperature limit. But we're working on releasing a much higher temperature version here in the near future. And you can see in these two upper images that the stem has been insulated, and we do require to meet that accuracy spec that the stem is insulated, and then we recommend insulating up and down ±6 inches from the transmitter itself to make sure you're getting the correct accuracy. So just to kind of recap, we talked a little bit about traditional temperature measurement points. We talked about alternative technologies, and we talked a lot about vibration and wake frequency calculations and best practices and how to do that. And it's just kind of a nice reminder at the end that Emerson, we have, uh, every step of the temperature product or temperature measurement point we can supply, and we can supply as an entire unit. So we can send you a Thermowell sensor transmitter combination that's been pre-assembled, pre-configured, ready to go, ready to just install and wire up or put in a power module and go. Um, and then we have a full slate of process connections and transmitter styles and sensor styles. So really, we can do it all. And then I'm not sure. Wanted to end a little earlier. We started a little late, so we're bumping up against our time limit here. Are there any other questions before we go?